discussion on potential, try to get a little bit better understanding of what potential is. And I'll say a lot of this material is taken from a fantastic paper called Potentially Confusing Potentials in Electrochemistry. So I highly recommend going and reviewing that. So what is electrode potential? Is it potential energy? Is it, electric fields? Is it electric potential? Is it electrochemical potential? Let's dive in and see. So we commonly in electrochemistry use two different potentials. So there's electric potential, and this is the path integral through the electric field. And this is all about fields. It's not about particles. And so that means it's not about electrons. We also have the electrochemical potential, and this is really what we are typically meaning when we say potential in electrochemistry. This is the potential that is, driving equilibrium. It's driving a lot of things. It's driving mass transfer, and in this case, electrochemical potential, unlike electric potential, it has to do with particles. So it's the electrochemical potential of a particle in a phase. So particle J in phase alpha, for example. Well, what makes up the electrochemical potential? We have the chemical potential, and then we actually add on a term that includes the electric potential as well. So this electric potential, it's actually part of what makes up the electrochemical potential. So we define the chemical potential here with no bar. That's the change of Gibbs free energy over the change of moles, and when we keep the temperature and the pressure and other chemical compositions constant. We can also write the chemical potential as a standard chemical potential plus the universal gas constant times temperature times the natural log of the activity of species J in phase alpha. And I'll just add that this is good for electrons, this is good for protons, ions, molecules, all of that. And so if we were to write the electrochemical potential completely out, then we would have a standard chemical potential. We'd have this term with the activity of species J. We'd have the charge of species J. So if it's an uncharged molecule, for example, then this term would be neglected in the electrochemical potential. But if it's an electron, then this would be -1, and then Faraday's constant and the electric potential in phase alpha. A few more points. So, like I said, for any uncharged species, the electrochemical potential and the chemical potential are the same. We can write out the activity of any species. Not the activity. We can write out the chemical potential of any species, and right here, this could be for a proton, this could be for an electron. Electrons do have activities in different phases. If it's a pure substance, then we'd say that our activity is equal to 1, and that would make it so that our chemical potential is equal to the reference state. And then we can write out, what would be the electrochemical potential for electrons in metals? Well, then we'd have our chemical potential of the electrons, and then we'd subtract off Faraday's constant times the electric field. Another thing is that the equilibrium between two phases for a certain species, what this equilibrium, the driving force for this equilibrium is that the electrochemical potentials become equal to each other. A few more properties of the electrochemical potential. Because it is linked to the chemical potential, it is intrinsically linked to Gibbs free energy. We also know that transport is governed by the gradient of electrochemical potential, specifically migration and diffusion. They're both governed by electrochemical potential differences. Convection isn't. It's driven by other forces. But typically in electrochemistry, we're often dealing in systems that only have migration or diffusion, or usually both. And then electrochemical potentials, they govern the equilibrium of any given species, and they also govern how chemical reactions happen. So we could write out the equilibrium between phases here, between phase alpha and phase beta, and then the equilibrium of this reaction we could write out this way. And I think I misspoke here. I said that it was common to have diffusion and migration both in electrochemical measurements. The truth is usually we set up our experiments in a way that we only have diffusion in our measurements. And it's actually more common to have convection in an electrochemical measurement than it is to have migration. So let's jump into a few examples with electrochemical potential. Let's say we have a metal junction, and we're going to call one of these metals alpha and one of these metals beta. Well, what will we see? We will have different work functions. Let's say we have two different metals here. We have metal alpha and metal beta. And because they have different work functions, or the energy that's required for us to move an electron from outside of that metal to inside of that metal, it means that we're going to have a difference in electric potential once the electrochemical potential equilibrium is established. So charge will be transferred as electrons move between alpha and beta until the equilibrium potential is balanced. But what that means is that we'll have a difference in the electric potential between these two phases, even at equilibrium. Well, what happens if we separate it out? So we have an electrode and then an electrolyte and then another electrode. So alpha being an electrode, beta being the solution, and then the electrode being gamma. Well, what we'd see is if we write out the electrochemical potential for the electrons in the solution, these are going to, processes are going to occur until the electrochemical potential of all three phases is in equilibrium. And what we'll see then is that we'll see a difference in the electric field as we move through. And here, the electric field will be constant in phase alpha, and then we'll have a decay down as we go into the solution. We'll come across and have another decay down at the interface between beta and gamma. And this electric field, this is going to play a large role in migration. So this is an important thing to note, is talking about liquid junction potentials. These are established by electrochemical potentials as well. So this is an experience that Devin Rapley, my advisor, had in graduate school. He was working on reference electrodes for molten salts, and he thought, hey, wait, I know how to make it so that the activity of our silver chloride reference electrodes and molten salts isn't changing anymore. Let's make it pure silver chloride. And this will fix the activities. Then we'll know for sure what potential our reference electrode is at. But the problem was that the membrane, it allowed chlorine to move across it, but it didn't allow larger ions like silver ions to move across it. And that meant that he wasn't able to establish an equilibrium between the silver plus ions in alpha and the very, very minute amount of silver ions in beta, because that transfer is so slow through the membrane. And that caused a massive junction potential between his reference electrode and the working electrode. And it was in a way that was uncalculatable. And so he wasn't able to figure out a way to get the liquid junction potential to work, or to get the 100 mole percent silver chloride reference electrode to work, because of the massive junction potential. And so essentially what you need to know is that junction potentials form when you have two liquids or two phases that are very different from each other. And it's something to look out for whenever you have membranes in your system. Okay, these are the questions that I'd like you to give a shot at before I go ahead and give you the answers. So go ahead now and pause your video, and then I'll give the answer in a few seconds. All right, so what's the relationship between electric potential and electrochemical potential and chemical potential? So electrochemical potential is built out from the terms for chemical potential and electric potential inside of a given phase for a given species. But which of these three potentials establishes an equilibrium in electrochemical cells? Well, it's the electrochemical potential. And this is in force even when we neglect electric fields, don't have charged species, because the electrochemical potential will just simplify to the chemical potential at that point. Okay, well, thanks for tuning in to Lesson 2. And we hope that you'll join us next time as we dive into Lesson 3, which is all about electrochemical kinetics. Thanks.